Welcome back. The second session today is started by Daeyeon Lee, who's going to be speaking about extreme nanoconfinement. Thank you very much.
Well, thank you very much for the introduction and also giving me the opportunity to share our work that my group has been working on for about 10 years now. And it's also great to be out of state right now. Some of you may know that there's apparently an election that's coming up in the US, and the state that I'm coming from is going to play a pretty important role. So all the mass media that you can think of is just flooded with political ads that are absolutely mind-numbing. So great to be in this environment to learn a lot of new things. So I'm going to tell you what this is, but my original interest in this research was actually making polymer nanoparticle composites. So they're everywhere, and we are in particular interested in making these polymer nanocomposites in the form of membranes, coatings, and films. So a lot of the materials that are commercialized and that are widely used right now have very small fraction of nanoparticles in the polymer matrix. The type of polymer nanoparticle composite that I'm interested in making are ones where nanoparticle phase is actually greater than the 50%. So nanoparticle phase forms the majority phase. And the reason that this is interesting is illustrated in some of these natural composites that you see here. A lot of those natural composites have these cross properties. You know, they have high toughness as well as high hardness, which are two properties that are often in conflict with each other. You can also imagine, making materials that have high gas barrier properties. The challenge with making these materials is that when you try to add large concentration, high concentrations of nanoparticles into polymer matrix and try to process these, the viscosity is extremely high, so the processing becomes very, very difficult. Okay, so that's why it's not so easy to make composites that look like these. So we wanted to see if there is a way to get there without using these very labor and energy intensive processes. So this is where we start with. Okay, this is what I showed you on my title slide. So this is a substrate, and then I have a polymer layer here. Okay, it's a glassy polymer, in this case polystyrene. On top of that, we spin coat nanoparticle from aqueous suspension. So these are, I believe these were 20 nanometer, 30 nanometer titanium nanoparticles. Okay? And then we do one of two things, very simple. One, we take this material, now this bilayer, and then put that in an oven. When we put this in an oven and heat this above the glass transition temperature of the polymer now undergoes capillarized infiltration into the interstitial pores of the nanoparticle packing. And as you can see here, when this happens, it almost looks like this nanoparticle layer sinks into the polymer layer, but it's not gravity driven because at some point it stops. I don't know if you can see it, but there's still a residual polymer layer here, but the nanoparticle layer stops sinking. So this is capillary driven. Okay? And I'll show you more quantitatively later, but the thickness of this nanoparticle layers stays more or less constant, which means that the particle-particle distance does not change. The volume fraction of the particle does not change after the polymer has gone in. So the particle packing has approximately 64 volume% of nanoparticles. It's essentially random closed packing of spheres. So at the end of the day, you have this composite that you generate very simply by just heating it, and you end up with 64 volume% of nanoparticles. Second way we can get there is instead of using heat, some polymers degrade before they become fluidized. So we expose this bilayer into a solvent vapor rich environment. What happens in such a case is that the solvent vapor undergoes something known as capillary condensation. So it condenses within the particle packing. If the solvent is a good solvent, this solvent now diffuses into the polymer, and now the polymers are able to infiltrate into the solvent-filled pores. And once you've removed the solvent, you again end up with these very, very highly loaded nanocomposite materials. So of course, as an engineer, I'm extremely interested about the properties of these materials. But while working on this, I started to think about some of the problems that come up. What's really interesting about this nanoparticle packing is it's porous. The characteristic pores of random closed packed spheres is known to be approximately 30% of the size of the particles. So if your particle size is 10 nanometers, you have on the order of 3 nanometer pores. And we've actually experimentally confirmed this in collaboration with Stefan Golden, who was at UCL at the time, using ellipsometric porosimetry. Okay? So you can see that as we change the size of nanoparticles that we are using, the size of the pore changes systematically. There is, of course, distribution of pore sizes, but characteristic pore size can be very well defined by just simply changing the nanoparticles. Then, of course, the size of the polymer can be varied by just choosing polymers of different length. So by doing this, what we can do is we can define something called confinement ratio, which is the ratio between the characteristic size of the polymer to that of the pore. And by doing this, we can span a very large ratios from 0.1 to up to 50 or larger. Very easy. Okay? So what we can do is, using this fairly simple system and fairly simple experimental procedure, we can now start to ask ourselves very fundamental questions. Okay, so here are some of the questions. And I hope that I can get through these questions. I'll share with you some of the things that we've learned. You can ask yourself, what would happen if we change the interactions between the polymer and the nanoparticle? Would that accelerate or slow down the infiltration of the polymers? Right? In line with the theme of this session, I'll address this issue in different aspects. For example, effect of surface polymer interactions on the mechanics of these materials. All right, so let me start out by looking at the effective confinement on the dynamics of infiltration. So how do we monitor the dynamics of this process? It's actually very easy. Okay, we take our bilayer. So all of the particles that I'm going to show you are silica now, and the polymer that I'll be using, featuring a lot, is polystyrene. Okay, we take this bilayer and then we put it on a hot stage, and then we take it to ellipsometer, and then we heat it. When you heat it again, the polymer undergoes capillarized infiltration. Okay, and then we can now monitor the thicknesses of these 3 different layers: the empty nanoparticle layer, composite layer, and the polymer layer. Okay, so this is what it looks like. As you can see, the composite layer goes from 0 to some thickness, and nanoparticle and polymer layer thicknesses go down. What you'll see is that if you add this red curve and the green curve, it's more or less constant, right? Again, showing that this particle layer does not swell. It stays, constant, meaning that you retain the original volume fraction and structure of that particle layer. And after we do this, what we do is we use, the Lucas-Washburn equation to basically relate the height change as function of time. And what we can do is, by plotting this now, this red curve, as h squared versus t, we can get this prefactor. Now, we can make some assumptions about the surface tension, pore size, contact angle of the polymer on the particle surface, which we now directly measure. Okay, we can infer what the effective viscosity of this polymer that is going through these pores are. Okay, so that's what we do to measure what is the effective viscosity of this polymer that is going through this capillarized infiltration, and then we compare that to the bulk melted state viscosity of the same polymer at the same temperature. So here's the result. So this one plot, I showed this one plot, but this is really results of 2 PhD theses. Okay, these 2 students. So I have 2 different cases here. So again, this is the effective viscosity that I got from Lucas-Washburn. That's the bulk viscosity in melted state at the same temperature. And this is the confinement ratio between the characteristic size of the polymer to that of the pore. When we have very short polystyrene that are unentangled in its melt state, and we see what happens to this normalized viscosity, you see that it actually goes up, and then plateaus at some value when it hits confinement ratio of 1. Okay? Now, interestingly, when we go to very, very large polymers that are very, very highly entangled in its melt state and do the exact same experiment, what we see is that this effective viscosity when compared to the bulk viscosity is much, much smaller. It's as small as 3 or 4 orders of magnitude. So polymers are able to move much faster than what you'd expect from the bulk state. So it was interesting that when we were doing this study, we came across this study, which was done by Zhou, and also in collaboration with Masao Doi, who was a close collaborator of Sum Edwards. Okay. What they've done in their experiments is that they used aluminum oxide membrane. So these have cylindrical pores, very well-defined cylindrical pores. Okay, and they did pretty much the same experiment using, in this case, polyethylene oxide to induce capillary rise. And what they see in their experiments, so these dots are experimental results, and the solid line that you see is the model that they came up with, which is shown here. And basically, they define that there are 2 possible ways that the effective viscosity of these polymers can be affected. One is where the polymer is infiltrating, and now there's this layer of polymer that is coated and stuck on the surface of the pore. So that effectively decreases the size of the pore. Okay? So that is going to effectively increase the viscosity. But then there's this other effect where polymer is now replicating through this network of polymers, where the network of polymers also is driven by the capillary pressure. Okay? So there's convective movement of the polymer network that is moving, and there's reptation. So that they attribute to this, this region where you actually can see that the effective viscosity is smaller than that of the bulk viscosity. Okay, so the result that I just shared with you from our own lab, my own lab, seemed to agree with this picture quite well. But then I had third student that worked on the same problem. Okay, and this is what he saw. Okay, notice that the x-axis is a little different here. So this is Tian, who basically kept polymers molecular weight the same here. So we also introduced polyethylene here, and saw that when we go to smaller and smaller pores, now the effective viscosity is increasing, right? It's supposed to decrease, but it's increasing now, which doesn't agree with the picture that we originally had, and also was proposed by Jia and coworkers. So we went back to that original derivation that Jia Zhou and Masao Doi had proposed, and just took a look at it, careful look at it. And so they're basically saying, we have a polymer that is rotating through this network that is under the influence of capillary pressure. Okay? And what we basically decided to do is, let's see if there are ways that we can refine this model. Okay, I'm an experimentalist, so this is not from scratch, but we took their model and basically said, okay, there are parameters here that should depend very strongly on the effective confinement. Okay, so for example, the primitive contour length of the polymer should likely change when the polymer gets confined. Friction coefficient between the polymer and the pore should also be affected. This was actually work done by Francois Brochard with Dujan. So we introduced these factors into the same derivation that was introduced. And here's what we saw. So again, this is now inverse of pore, and here's the normalized viscosity that we obtain. So the filled symbols are our own results. The open symbols are the results from the other papers. Okay? What you see is that now by making those modifications or refining the model that I just showed you, we can explain this rise in the viscosity as the pore gets really, really small. Okay? We can also go back to the experimental results from the prior work, and what you see is that they also seem to see that increase, okay, when the pore size got very, very small for their own polymers as well. So this refinement now tells us that there are actually 3 different regimes, right? There's a regime where the dead zone on the pore affects the polymer infiltration, and then this is the reptation in the capillary pressure-driven flow, and then there's region where the confinement affects many of the parameter that affects how these polymers are behaving in these pores. All right, let me tell you a slightly different story here. So this is a case, instead of heat, we now use solvent. So we use this acronym, solvent-driven infiltration of polymers. So we take the bilayer, we expose it to vapor of the solvent. Vapor undergoes capillary condensation, and then that induces infiltration of polymer. Now, what we wanted to study here is, how does the effect of the interface, essentially, interaction strengths between the nanoparticle and polymer affect the rate at which the polymer infiltrates into these solvent-filled pores. Okay? So although I'm an experimentalist, this was a perfect project to do computational research, right? It's very difficult to keep everything the same, but just change the interaction strengths between the polymer and the surface. So I collaborated with Rob Riggleman. I have a very talented student who did both experiments and computational studies. So we made essentially, we made a computational model of what our system looks like. These are the nanoparticle packings. That's the polymer. Solvent is filled, but I've removed those, so we can see what happens to the polymer as we change the interaction strengths between the nanoparticle and the polymer. Okay, so this is stronger interactions between the two species. And we can, run these simulations. Okay. And then what we can do is we can take a look at what the effect of strength of polymer nanoparticle interaction is. So as you go from left to right, stronger interaction. And this shows where the front of that polymer infiltrating polymer species are, the very front, okay, at different time points, okay? So what you see is that when the strength of interaction is fairly weak, there's some rate. But as we strengthen that interaction, it actually goes in faster. But then when you further strengthen that interaction so that they become more stickier, it actually slows down. Okay, so it's not monotonic. So this was great, but what we wanted to do is, gain more fundamental understanding of what's really happening here. So we wanted to really break this down to very, very simple fundamental unit. So this is where we did a lot of reading, and we learned about this entropy barrier model that was very well developed by Muthukumar. So basically, the story is the following. We imagine that there are two cavities, and these two cavities are connected by what we call small nanopore. Okay? And we basically have a polymer that resides in cavity 1, and I want to calculate time for it for this chain to go from cavity 1 to 2. It will do that by snaking this end and then translating some subunits of this polymer into the second cavity, right? What we can do is we can calculate the free energy of different states using self-consistent mean field theory, okay? And then use this Fokker-Planck formalism to go from free energy, which will give you a probability of each state, to basically learn and understand how the kinetics would change as you change the interaction strengths between the polymer and the surface of that cavity. Okay, so that's what we did. And here's the free energy profile. So again, this is a polymer with n units, and I'm going to put m units in the second cavity. Okay, so when you go from 0 to 100, that's when you have full translocation. So when you have very weak interaction between the polymer and the surface, what the polymer wants to do is it wants to maximize the volume that it takes up. Okay, so when the polymer has half of its segment in the second pore and the other half in the first pore, you have the lowest energy state, so that you see a big energy well there. When the polymer is very sticky to the surface of the pore, what the polymer wants to do is it wants to minimize the area volume that it spreads itself while sticking to the surface. So the polymer would rather stay in one pore, so that's why you see this big energy minima when the polymer is completely in one pore, one cavity or the other cavity. Okay? So somewhere in between, you have this free energy profile where it's fairly flat. Okay? So what is the net result of this? Net result of this is that when you have polymers that are not very sticky, you have some translocation time. And then when it becomes very sticky, again, it wants to stay in the first pore. So it takes very long time for it to go into the second pore. So in the first regime, you have polymer that is swimming through the pores that are solvent filled. Whereas in the second case, the polymer now has to climb by sticking to the surface. Okay, and I had a very creative student. In between, what we have is what she calls Little Mermaid regime, where you can either climb or swim. So you can take advantage of those both mechanisms to undergo infiltration. And that's why we see this enhanced infiltration dynamics. All right, so I'm going to go to thermodynamics now. Okay, so I've shown you how confinement and surface polymer interactions can impact the dynamics of infiltration. So here what we are studying is, what does confinement do to the miscibility of polymer blends? As many of you know, polymer blends do not like to mix because the entropy doesn't help very much, right? So let's say, and we can do this experimentally also, but I'm going to show you some computational work, okay? Let's say we take polymer blend AB, okay, made out of two polymers that have the exact same molecular weight, and then we infiltrate them, okay? What will happen to the phase behavior, okay, the miscibility of the two polymers? So again, we rely on computational methods. Here we take basically self-consistent field theory, and my colleague Rob Rigerman has been really developing this method to look at these heterogeneous systems that have particles and polymers, okay? So to model polymer, we basically say there's a solid core polymer, and the interface actually has this decay in its profile, okay? And this is the simulations box. So we have particle that is packed in square array, and we basically put two polymers in there and see how they behave. All right, so this is the typical polymer phase diagram, and we're looking at a symmetric system here, okay? So we take polymer A and B, and a key point here is that those two polymers have neutral interactions with the particle, meaning the particle does not favor one over the other. They have the same strength of interactions, okay? And if we put the polymer blend where they're supposed to be well mixed, and we run this simulation, you'll see that A and B both distributes homogeneously in these four interstitial pores. If we go up in chi n and then put this in a region where you expect polymer separation, that's what you see. You see a region that is rich in A, component A, and also rich in component B, meaning that there is phase separation. Okay? So we basically run these simulations now in a way that the polymer gets very, very confined within these pores. Okay? And here is the result. So there's a lot going on here, but in summary, what happens is as you confine these two polymers in these pores, and the surface of the pore is neutrally interacting with the two polymers, what you see is that the miscibility window increases dramatically. Okay, so the phase boundary moves upward in chi n. Okay, so why is this happening? This is interesting, but why is this happening? So we looked at different factors. So let's first take a look at how the enthalpy of mixing should change. When there's a demixing that occurs, right, the enthalpy should decrease, right? Because AB contacts now are replaced with AA or BB contacts. So that's what you see. So if we look at what would be expected from Fleury-Hagen prediction, okay, so let's just take a look at one example. So this gamma, again, is the confinement ratio, okay? As you increase chi n, at some point, you're going to see phase separation and enthalpy decreasing. What we see in our simulations is that it's actually much smaller. That enthalpy reduction is much smaller, okay? So why is that? So basically, what's happening is right around the particles, okay? Right around the particle. I told you that there's a sort of this decay, okay, sigmoidal decay in the profile of the surface. So there are sites, lattice sites, that cannot be occupied by these monomers. So that effectively decreases the coordination number of the polymers. So that's why you now have less AB contacts. Okay, so that's why the enthalpic now interaction favors mixed state. All right, how about and we can now account for the surface effect, right? Because we know exactly the geometry, and that's the solid line that you see. If we take into account the surface effect, we can now take a look at how that affects the enthalpic interactions. How about entropy? When demixing occurs, entropy should decrease. It should increase, right? No, decrease. So this is what we see. So let's take a look at one example here. Okay, so Fourier-Hagen prediction would give you that prediction, but when we look at how much entropy change takes place, it's much significantly larger. Okay, so why is this happening? The reason that this is happening is, as I told you, okay, right around the surface has neutral interactions between A and B. So right around the surface, the polymers want to maintain 50-50 mixture, but as it undergoes phase separation, in the center of the pore, the concentration will be far away from 50-50 mixture. So you essentially develop this concentration gradient, and this concentration gradient now affects the entropy. So that's the effect of entropy and enthalpy now both favor the polymers to stay mixed in these highly confined systems. All right, so I think I'm doing okay with the time. So I'm going to go to the third topic now, which is something that I was very, very much interested in, right? How does confinement and the interactions between the polymer and the nanoparticle affect mechanical properties of these composites? The particular property that we are interested in is fracture toughness. It's basically how much does the material resist fracture, which is catastrophic failure. Okay, so Kevin Turner, my colleague in mechanical engineering, I had a very talented student who was able to perform this double cantilever beam test. It's a test that's been really exploited by Dausgaard at Stanford, where what we want to do is we want to propagate crack through over a long distance in order to get a reliable measurement. So what we do is we make this sandwich sample where our composite film are sandwiched between two very, very stiff beams. These are silicon wafer, basically, okay? And then we induce fracture and then let the crack propagate through our film, okay? And we measure the response, okay? The way this is done is that we propagate the film a little bit and then we let it go. So there's a load and then we let it go and then we do it repeatedly, okay? So the crack propagation is pretty stable. And from this load displacement curve, we can get this G sub C, which is the fracture toughness data. Okay, it's very reliable, but very tricky experiments. Eway was just a master at doing this. All right, so let me first talk about the confinement effect. Okay, so we have polystyrene, and its molecular weight increases as you go from left to right. This is the fracture toughness. And as you can expect, for a given nanoparticle size, as you increase the molecular weight, the toughness goes up. So that's not that surprising, right? And that is true for all different types of nanoparticles, okay? As you increase the molecular weight, the toughness goes up in general. Now, Eway was not just a good experimentalist, she thought a lot about her results. So she took this data and plotted it slightly differently, okay? It's the same graph, but here what's being plotted is, it's the fracture toughness, and for a given polymer, she's changing the size of nanoparticles. And you see two completely different behavior, right? For these smaller particles, as you go to higher and higher, larger and larger particles, toughness actually goes down, whereas for these longer polymers, you see toughening happening. Okay, so this is an indication there are potentially two different mechanisms that are competing against each other. So here's the picture that we have, okay? When you have polymers, particles that are very small, that means the pores are very, very small, right? So in such a scenario, the polymer has to be stretched, okay? They have to be very stretched. So in this case, what would likely lead to toughening is when the polymer gets longer and longer, it bridges multiple particles, okay? And this bridging now induces toughening of the composite material. However, if the particles are fairly large, that means the confinement ratio is not very high. Okay, so the polymers don't really have to stretch very much. In such a case, within these interstitial pores, you can still retain some of the entanglements. Okay, so it's these entanglements that are remaining within the pores that leads to toughening. So for larger particles, it's the entanglement within the pores that leads to toughening. Whereas for smaller particles, it's the stretched polymer chains that are able to bridge multiple particles that leads to toughening of these materials. And that's the picture we have. So what about if we change that interface now, right? Interactions between the polymer and the nanoparticle. And let's see what the effect is. All right, so for small particles, so what we did here is we took silica and polystyrene, and then we, to weaken that interactions, we passivated the silica surface with some silane grooves, okay, so that the strength of interaction is much weaker. Okay, and for small particle case, what we see is that toughness indeed does decrease. Okay, so that's what you see here. The red is when you have silica and polystyrene. Green is when you have silica with passivated silica. I'm sorry, polystyrene with passivated silica. And you see that there is decrease in the toughness of these materials. And that's understandable. For small particles, like I said, it's the bridging that dominates the toughening mechanism. So when you weaken that interface, your toughness is not as high. Now, for larger particles, the story changes. Okay, so we now have two cases where we can take polystyrene, and then we can now replace that with poly-2-vinyl pyridone, which has this hydrogen bonding interactions. Okay, and we can also weaken the interactions between poly-2-vinyl pyridone and silica by doing passivation. And what you see is that there's, some difference, but not significantly large difference. Okay. In fact, what we learned is that if we go to a polymer that has very, very high intrinsic toughness, that gives you the highest toughness for these materials. And that, again, is because we believe these remaining entanglements within these pores are playing a very important role in toughening these materials. Do I have another 3 minutes, or should I finish? Two, okay. So, okay, I was going to skip this, but since I have 2 minutes, I'll tell you about a story that we don't fully understand. Okay, I'm going back to the infiltration dynamics. Okay, what we do here is we create a statistical copolymer of two monomers, where one monomer is not very sticky, the other one is very sticky. Okay, so it's a random copolymer. One is not very sticky, the other is very sticky. And then we measure how long it takes for the polymer to infiltrate the material. Okay, so this is a very sticky polymer, all P2VP, and this is polystyrene, not very sticky. And let's see what happens in between. So this is time it takes to fully infiltrate my particle packing. Do you want to see what the result is, or should I go to the conclusion? Okay, so we see this non-monotonic behavior. Okay, and we try to see, is it the bulk viscosity that is, doing this? Because bulk viscosity, doesn't change a whole lot. Glass transition does change a little bit, but it really doesn't, explain this, up and down trend that we are seeing. So this is still a big mystery to us. I think there are a lot of people that could advise us on what might be happening. So I'd love to hear your thoughts on this. Okay, with that, I'll conclude my talk by telling you that when the polymers are confined and there's a lot of interactions between the particle phase and the polymer, the trends that we see are often non-monotonic, okay, and a lot of times context dependent. And we've seen this in the infiltration dynamics as well as the thermodynamics and mechanical properties. And we believe there are a lot of more interesting, very fundamental soft matter physics questions that we can address. With that, I'd like to thank the students that have done the work, as well as my colleagues at Penn who have helped us in various different ways. Thank you very much.
Thank you very much. Questions, please. Yes.
Random copolymers. Sequence. Yeah, I mean, that's exactly what we like to do. I mean, you know, what we've done is we've taken diblock copolymers and then random copolymers of the same composition, and they also show very different infiltration dynamics. Yeah, so that would not describe what we are seeing, right? If it's just a net average, you know, some linear average or some kind of mean average interactions between the polymer chain and the nanoparticle, we should see a linear trend, but we don't. So yeah, I don't know how to account for that. Can you repeat your question? Oh, yeah, yeah. Yeah, 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 yeah. Yeah, yeah. It actually went the other way, though. In the other case, as we went from weak to intermediate to strong, it sped up, right? Here, it's actually slowing down and then speeding up again. So it's actually exactly opposite of what we saw when we had solvent present in the system.
Viscosity was monotonic with regards to cleanings. I think that is the result is somehow was anticipated and is expected. So it's a nice thing. Why would people expect that? In a confined situation, the polymer chains do not have Gaussian statistics. They're swollen. And in your specific situation, there will be logarithmic corrections. So it will increase logarithmically with n, but with a large prefactor, which is a superposition of all the different distances polymer experience in your system. And because the chains are larger, because of this logarithmic correction, if you rework rotation theory, so the space, the real space is explored more efficiently. So the dynamics gets faster and the viscosity goes down. So that would normally mean a logarithmic progression, but I suppose that is not a contradiction to the power laws you fit it. So it somehow it fits in the picture we would have.
Yeah, so the power law and I think decreased viscosity is something that I think fits the picture. It's again, when you even further confine the polymer, then the viscosity again goes up. I think that's something that we weren't expecting.
Thank you. Let's thank the speaker again.
Thank you.